Hi friends, welcome to GMK tutorials. In this video, we are going to study about the field effect transistor. In our previous video, just we will see the just a very brief introduction about the what is meant by PN junction diode, how the PN junction diode is going to be operated, as well as how transistor is going to be working with the help of the some basic diagrams. So in this video, just we will see the what is meant by field effect transistor. So field effect transistor is one of the most widely used element in the IC fabrication. So let us see just why we are using the field effect transistor. Just we will see what are the differences in case of the BJT and field effect transistor. In case of the field effect transistor, the current is due to majority charge carriers. Okay, current is due to majority charge carriers. So it is called unipolar device. Unipolar device. As well as one more difference in case of the field effect transistor compared to the bipolar junction transistor, that is nothing but the size of the FET is 1 by 5th of BJT. So more number of field effect transistor can be fabricated in the single semiconductor die compared to the BJT, as well as it is also unipolar device because of in case of the field effect transistor the only one current is responsible for current produced in the channel. So that is nothing but whether it is a majority charge carriers of electrons or majority charge carriers of the holes. It may be any one of them. So but in case of the BJT, the current is with respect to the both majority and minority charge carriers. So that's why it is called as a bipolar junction transistor, but we will call it is a unipolar device. As well as let us see one more difference. So FET is nothing but field effect transistor. So field effect transistor, that means the applied voltage at the gate terminals, so VGS is the responsible for current flow in the corresponding field effect transistor. That's why we can call as a field effect transistor. As well as the field effect transistor is a voltage control device. Okay, the flow of current in the field effected transistor can be controlled with the help of a voltage across the gate terminal. So the field effected transistor is also called as a voltage controlled device. Voltage controlled device. Okay, the size of the field effected transistor very small, so it can be used in many applications. Okay, so these are the some of the uh, basic reasons why field effect transistor is very famous compared to the bipolar junction transistor. Okay, as well as the fabrication is also very easy. Fabrication of field effector, fabrication is easy, as well as operation of the field effector transistor is also very simple compared to the bipolar junction transistor. So those are the some of the reasons why field effector transistor is very famous compared to the bipolar junction transistor, right? Now let's move on to the very deep into the field effector transistor. In case of the field effect transistor, let us see the classification. Okay, types of FETs. Okay, generally the field effector transistor can be classified into two types, that is nothing but JFET, and second one is nothing but a MOSFET. JFET is nothing but junction field effect transistor, and MOSFET means that metal oxide semiconductor field effect transistor. Okay, instead of studying the metal oxide semiconductor field effect transistor, just we will see about the what is meant by JFET. So JFET is nothing but a junction field effect transistor. Okay, let us see the JFET construction. JFET. So the construction of the JFET is very easy also. So let us see the diagram. Just you will take one N-type bar, P-type semiconductor bar. So here I will consider N-channel bar. Okay. So and the two sides of the N-channel bar, just you will dope very heavily P-type regions on the both sides of the N-type channel. So this is a P-type material. This is also a, so just will redraw the circuit. It is not that much of the better. Okay. So in the both sides of this, just you have to dope the P-type region to P-type regions on both sides of the. Okay, this is the contact. So this device is also internally connected to this one. Okay, internally connected to this one, right? Now let us see the, this is a very this is nothing but a P-type semiconductor materials. Okay, as well as this is also connected to the VGS, negative, positive. So this terminal is connected to the source. This is source. This is drain. So now this drain is also connected to this source. So that is nothing but VDS, negative and positive, plus minus. This is generally called as a VGS. This is generally called as a VGS. This is generally called as a VDS. Right? So here what happens is that initially if we treat VGS is equal to 0, okay, so just I will mention here, when VGS is equal to 0, what happens is that so this P-type and N-type channel forms, this is a N channel, right? Therefore it forms as a P-type semiconductor PN junction. It forms as a two PN junctions on the both sides of the N-type semiconductor bar. Here what happens is that when the VGS voltage is equal to 0 means that, so this is that this negative terminal is connected to the positive P-type semiconductor material. Therefore this P-type and N-type regions are in the reverse bias condition. Under the reverse bias condition, what happens is that the depletion region is increases. Therefore the depletion region of this material is increases. Okay, as well as this is also like this. So on both sides, because of just these two are internally connected. Okay, this is a depletion region. So this is also a depletion. So this is also a depletion region. So still if you are considering VGS is equal to 0 consideration. Suppose if the VGS voltage, if the VGS voltage is still increases, VGS is equal to more negative, what happens is that the still depletion region with this increases maximum. Okay, as well as this depletion region width is increases. This depletion region width is also very easy, guys. Just if you are concentrating here, it is a very small, very dead easy, very small topic. As well as this is also very easy concept also. So still if you are increasing the VGS more negative, the depletion region width of the increases. But at particular point of time, Okay, at particular point of time, those two depletion regions are contact each other. At particular point of time, those two depletion regions are constant. Okay, those two depletion regions are constant. Okay, constant means that those two depletion regions are contact each other. Sorry, those two depletion regions are constant, not a constant. It is a contact. Two depletion regions are contact. So ID is also constant. Okay, so let us see here. What happens is that at a particular point of time, those two depletion regions are contact each other, as well as the shape of the depletion region is also very important, because of it is more negative to, so depletion region width is less, but uh, here very less, so depletion region move towards the n channel very more. We know that generally in case of the depletion region is entering into the very lightly doped region compared to the highly doped region, right? So that's why the shape of the JFET is like this. Okay, so at a particular point of time, these two depletion regions of the junction field effect transistor are maybe contacted at each other at particular point of time. Okay, at a particular point of time, these two are maybe touch each other. So this is the ID current. This is the direction of the current. We can call as the ID current. Okay, this is the direction of the current. So this is very important, guys. Even though if you are increasing the VDS voltage at a particular time, even though if you are increasing a VDS value increases, suppose if you are taking VDS is also increases, ID constant. Okay, up to that point only, this drain characteristics exhibits some direction. Okay, so this is nothing but a junction field effect transistor. Okay, so let us see the some of the waveforms related to this one. ID, this is nothing but a drain current, it is in the form of a milliamps. So this is nothing but a VGS, gate to source voltage. So gate, sorry, it is nothing but a VDS, right? At at zero voltages, this value maintains at a zero voltages, increases, and it will maintains like, but it will increases like this. And here also same thing, like this, right? So this is the characteristics of the corresponding graph. So here when VGS is equal to 0, if the VGS is more negative, -1, -4, so this is nothing but positive cases, right? So this is a situation. So here this is generally called as a VDS actually, when the VDS, okay, this is generally called as a VDS drain to source voltage. Okay, VDS, this is the characteristics of this one. So this region is generally called as a, okay, this is generally called as saturation. This region generally called as a ohmic region. Ohmic region. This is generally called as a cutoff region. Cutoff region. These are the drain characteristics. These are the drain characteristics of the JFET. These are the drain characteristics of the JFET in case of the junction field effect transistor. Junction field effect transistor. I hope this video is very helpful for you guys. I think just it will give a very brief introduction about the how the construction of the junction field effect transistor and what about the operation of the junction field effect transistor also. Okay, right? I think all of you having some doubt will be there, sir. Why this ID current is maintained? So even though if you are increasing the some drain current, what happens is that these two are contact each other. So the current is the maximum at this point only. Okay, this is the completely depletion region, right? At a particular point of time, this maintains a, okay, this is also a, these two are contact each other. So this is completely depletion region, right? This is also a completely depletion. This is also a depletion. These 2 points are connected at particular point of time, right? So after that, this ID current maintains a constant. So in case of the saturation region, it maintains a some constant curve. So this is a reason. After ohmic region, at a particular point of time, these two contacts are make as a, so this is generally called as a VP. That VP is generally called as a pinch off voltage. Pinch off voltage means that the voltage at which those two depletion regions are contact each other. That point is generally called as a pinch off voltage in case of the junction field effect transistor, right? So thank you guys. Thank you for watching GMP tutorials.